Hi, everyone. It's a pleasure to be here. I would like to begin by asking you, the audience, one question. Did you ever own one of these? This is the Nokia 1100. It came out in 2003, and I used to own one. I remember that even though it had a battery of 850 milliamp hours, I would be able to use it for multiple days at a time without needing to recharge it, which was wonderful. But nowadays, your cell phone most likely looks something like this. This is the iPhone 12 Pro Max, which came out a few months ago. And like most smartphones, it probably won't even last you a single day, even though the battery at more than 3,600 milliamp hours is more than 4 times the battery of the Nokia 1100. So naturally, the iPhone can do many more things than the Nokia 1110. But with this example, what I want to show is that there's a general trend that as the functionality of an electronic device increases, so does the cost, not just of the entire device and the components that are used, but also of the battery in terms of the size that it needs to have, as well as the environmental impact in manufacturing all of these components. So this is a trend that in general, even though it has happened in not just the cell phone market, but in others as well, is something that is probably going to have a limitation on the IoT. So in the Internet of Things, we also want to add functionality. And we want to add this functionality so that our environments and our devices are smarter. And we want to do this at many different levels. So this can come at just the level of the user, that, in the quantified self, we want to know how many steps we take and other variables. Also at the level of the smart home, where we have multiple devices connected to our smart home that we can control, but also in smart cities. And currently, our sensing devices look somewhat like this. In fact, there's a running joke in the industry that sensing devices are a big battery with a little bit of silicon on top. And you can see why. In certain cases, depending on your application, your battery can be up to 90% of the volume. And in case you need special batteries, it can maybe be 50% of the cost. So in general, with my research, my goal has been to make smart devices in a way that is cost effective, maintenance free, and environmentally friendly, hopefully, if we get to take away the battery. So this is what I've been doing for the past few years. Let me then tell you a little bit about myself, although most of it was covered in the introduction. My name is Andrés Gómez. I'm very happy to be here, and I want to thank you all for the invitation. I'm originally from New York City, born and raised, but as you saw earlier, my heritage comes from a different country, so I'm Colombian American. I'm currently a postdoc fellow in St. Gallen. Fairly recently, I decided to come back to academia after a short stint in industry. So in industry, I was in Minomico for a couple of years, where I worked on different topics, low power sensing and low power networks, and things like this. Afterwards, I did do my PhD in two groups. I split my time 75% and 75% among the two floors, and has been energy-driven design. So let me first tell you about what I call steady state design. So here we generally in these sensing devices have three different things. First is a stable source, which can be a primary battery, or it can also be a rechargeable battery, but it's something stable that will always have a nice output voltage. And this powers on an application circuit, which has some different types of sensors, it has some processor, and it has some way to communicate through a low power radio. And from this application circuit, we then get some information on the other side, depending on what type of technology you use. It might be on your cell phone or on the cloud. But in general, it provides us with information that we're interested in. So when we look at these different blocks, on the left, the stable source, to have a big battery that lasts for a while, is expensive because the way things are connected to the application circuit, things are generally always powered. You might have sleep mode, but there's still a voltage in there and you're still consuming something, even if it's nanowatts. But we are happy to pay all of this if we have a deterministic information flow. So we might be interested in having sensor readings every hour or every 10 minutes. And with a big battery, even though it's expensive, we know that we can have this. So the key feature of this design paradigm, having this steady state, is that our energy will be continuously available and we can freely choose when we consume this energy. And hopefully we have a very long lifetime. Hopefully it can get up to 10 years or so with the current technologies that we have. So this is a fairly traditional life cycle, and this is generally what it looks like. We think of our devices as something that we deploy or they have birth. After setting up the different parameters, they reach a level of maturity where they're in production and they're working. And as a designer, we ideally want this time to freeze and to stay there for an indefinite amount of time. But in the real world, things age. So our components age, and eventually at some point it gives out and they reach their end of service, and we would have to redeploy and gather them again and redeploy. So when you look at the component agent of this traditional steady state paradigm, there are many different points of failure. Now, silicon in general, if you look at data sheets, they say that it's fairly stable as long as you keep the right voltage, the right voltage and the right temperature conditions. In theory, it should last for millennia based on their aging tests. Solar panels as well can last for many decades, assuming that you take care of them and they're not out in a very harsh environment. So if things are nice, well taken care of, they should also last for certain decades. Energy storage, however, it's usually one of the weakest points in these sensors, because rechargeable batteries can usually only accommodate for hundreds of cycles. At some point, their storage capacity decreases to a state where you cannot really do anything useful. And if you have a primary battery, then the charge cycle is only one, because as soon as it's discharged, then you have to replace it. So this is one design component. This is one design paradigm, and I don't think that this is the only reasonable paradigm that one can have. So this is where energy-driven design comes in. So instead of having a steady state, it will be entirely driven by environmental energy. So everything stays pretty much the same. Just that the left-hand block, the source, is now not steady, but it's sporadic. And this is because the source is actually the combination of multiple things. It's the environment, which is where the primary energy comes from. Then we have a transducer, which converts this into electrical energy. And we have a small capacitor. So here we do also need to have some level of storage, and you'll see later on what I mean by this. But in general, these small SMD capacitors, if they're ceramic, these have very, very high reliability, and they're also designed to last for many, many, many years. So with this energy-driven design, our sporadic source, because we're no longer spending on a big battery, we can have things that are relatively cheap, but we do this at a price because our application circuit is not going to have continuous energy available. It's only going to be sporadically powered. So there will be times where it has literally 0 volts, 0 energy stored in the system. And this means that our information flow is no longer going to be deterministic, because if the environment doesn't provide any energy, it's simply dead. But there's a glimmer of hope, because it might be correlated, the energy availability of the environment, with the information that we're interested in. So we'll see some examples of this a bit later. The key feature then of this energy-driven paradigm is that the environment is the thing that provides this energy, not an element inside of the system. And the objective is then to minimize the wake-up time. And hopefully we can get down to a few seconds of the device being completely off at 0 volts to then start doing something when the environment provides it with energy. So to contrast these two, steady state versus energy-driven paradigms, I like to think of it as predictability versus resilience. So when we have a system and we want it to live as long as possible, we need something that I call an energy cycle. So we need this energy cycle or energy storage to be very large. And this is because we want the two states, full and empty, to be as far away as possible, so that it takes a very, very long time before we reach this empty state. And we have to change the system. When we have, it's nice that it takes a long time to discharge, but it also means that it's going to be very expensive to fully charge an empty device, simply because the two states are very far apart. So with this perspective of resilience, we want the system to actually wake up as quickly as possible, which means that we want to have this slow energy cycle Q. And when we have a small energy cycle, it means that full and empty are very close together, so that yes, okay, it discharges very quickly, but it also recharges very quickly. So this is a very nice property that the other system does not have. So when we want a predictable life, right, we need to use that live as long as possible approach, because it's very analogous to a human life, right? We wanted to extend for as long as possible. But with this resilient life that we have, when we do energy-driven design, we're actually designing little zombies that for the most part are dead, and they only wake up or come back to life as soon as there's a little bit of energy from the environment. So now I'm gonna go into more details about the lower level aspects of energy harvesting, and we'll build up towards applications later on. So the first thing that I have to say about energy harvesting is that there's a great power imbalance. So let me first draw an axis of power, and you can see that I go through many different orders of magnitude, from a few microwatts, a microwatt on the left-hand side to a full watt on the right-hand side. If I were to depict the different transducer technologies that we have available and we normalize them by their area, they usually sort out like this. So on the right-hand side, we have photovoltaics, which are the ones that generally have the highest power density. So if you have a solar cell that is out at noon near the equator, when it's sunny out, you'll probably get 10 milliwatts per square centimeters. So this is great, but it's only the maximum, right? In reality, most of the day, it's going to be significantly below that. And then you have many other technologies such as piezo, which also provides significant amount of energy. It depends on the material being deformed. And then you have thermal, which depends on thermal gradients, but all of these have, in general, lower power densities. So if we look, that's on the power generation side. If we look at the power consumption side of our actual devices, the picture is rather bleak, because depending on which components we have on our system, our active state, when these things are on and they're doing something, can very easily add up to hundreds of milliwatts. If you have a camera, if you have, a multi-core multiprocessor in there, if you have a radio, something besides Bluetooth is very low power, but if you have something like LoRaWAN or Wi-Fi, you're very easily going into the hundreds of milliwatts. But luckily, most of our electronics have something called the sleep state, which in the best case of scenarios is around 1 microwatt or maybe less, hundreds of nanowatts. And then we can leverage this sleep state to, on average, be the same as our input. So this is where we have sort of the equivalence of the energy input and the energy output. But it's not that easy to do, as we'll see a bit later. So when we're doing energy harvesting, since it's all driven by the environment, one of the first questions that we want to really know is to understand how much energy does a particular environment provide us with. So to do this, the best thing is to have some measurements, but this can be quite challenging. Just to show you how challenging it can be, here are two colleagues of mine, Lucas and Moritz, and this is a setup that we needed to do to record how much energy we would get from wearable TEGs that Moritz is wearing there on the left-hand side. So Lucas needed to carry a car battery, an AC inverter, to power the Keithley and Quayside power measurement units, and to hook all of this up so we can do measurements as Moritz was walking around in places. So this is very cumbersome. It's not that easy to do. And so to address this issue, Lucas and I decided that we wanted to do something about it, and we designed the Rocket Logger device to facilitate these types of in situ measurements. So the Rocket Logger device looks like this. It's based on a BeagleBone. You have a cape, and you have then some cables, which can then easily go to your components, and you can record how much energy your transducers are producing, and you can also consume how much your electronics are consuming. What's really nice about the rocket logger is that we do seamless auto ranging. So we can very accurately measure currents that are in the nanowatt range and the microwatt range, but we can also measure, this is for the sleep states in particular, but we can also have components that consume hundreds of milliamps, and we can do seamless auto ranging to have very accurate measurements on a very wide range. This Rocket Logger project is open source. You can go to this website, you can download the hardware, the software, and make your own device. It won an award from a German magazine, Design and Electronic, in 2018. And in fact, it's used by many different research groups in Europe and in the US as well. So with this rocket logger, once we have this, we finally had the right tools to ask the question, how much energy is available indoors? And to do this, then we decided to do a full measurement campaign for over 2 years with 6 indoor stations that would allow us to record multiple things. So this is what the indoor station looks like. We have the rocket logger there on the left, and then we have another special board there on the right, which has a standard Sanyo solar cell and some electronics, something called a virtual battery. It's basically just something that will allow us to ensure that you have always a specific voltage on the output of the boost converter, so that we can measure how much energy we would be able to harvest using a BQ chip. So we did this for many years. We published the data set. You have there a link available. And I'd like to go through some of the results from this measurement campaign. So some of you probably recognize this floor plan. This is the ETZ building, and in particular, this is the G floor. And you have the green dots, which represent the locations of the station, of the different stations. The north is pointing like upper left. And so let me take you first to the results from station 14, which is very close to the window, and it was facing east. So here what we have on the x-axis is the hour of the day. So what we did was we took all of the measurements from those 2.5 years, and we binned them per hour of the day, and then we took the average power. So here when you see the red, it means that that was a very common value for the average power at that hour. And so if we look at 6 a.m. in the bottom, it's mostly red because most of the time you don't harvest that much. But you do see that there is a peak that goes up to 6 milliwatts or so. And this is because during the summer days, when the sun was rising, there was a certain point in time where it was actually hitting directly the solar cell. And so you have this huge spike in your input power. If we look at another station here that was facing west, so we would have a similar peak, an upwards peak in the evening hours because it was facing west, but this peak is not so high. It's a bit the angle. It wasn't hitting so the sun was not hitting the solar cell directly. So the peak power that we saw there was around 1 milliwatt, which is a bit less, but still a fairly good amount. Then I'm going to show you also this station number 6. So this was far away from the window, so you didn't see the cycles of the sun. And you also see here that it's much flatter, so you don't have the peak. And the average consumption, the average power generation there was around 100 microwatts, so to speak. So it's significantly lower when it's based entirely from indoor lighting. And you even see this weird point outliers there, and that was actually me. This was my office, and this is I was writing my dissertation in 2018, and so we're gathering the data set at that time, and you actually see the peak that my office light was late until fairly late at night. So it's funny how you can see these periods pop up in the data set, and this gives you a little bit of a hint towards an alignment of human presence and the generation of energy. So to summarize, I showed you the distribution in terms of time, but if we only are interested in the energy that we were able to generate per day, we can summarize the results like this. So my old office, these are violin plots, which show you the minimum, the maximum, and the area shows you the distribution of the different daily energies. So my old office gave a maximum of 4.2 joules in one day. That was the maximum it gave in 2.5 years. And on average, it was something like 2.1 joules per day, which is a fairly good amount, I would say, even though it's fully powered from indoors. The one that was facing the northwest had a maximum of 19 joules, which is considerably larger. But the one that was facing east was the one by far that generated most on average, and partly because of those summer weeks where it was able to get very, very good sunlight. So we had a maximum of 79 joules, which is an enormous amount. And you'll see then what we can do with these amounts of energy when we look at applications a little bit later. But you might be wondering then, okay, this energy-driven paradigm, okay, it sounds interesting, but when can they really be useful? And they're most useful, and I would even make the claim they're optimal, that when you have this alignment between the information and the primary energy. And when you have this alignment, then all you need is a transducer to produce that electrical energy so that you can gather that information using the primary energy that the environment was providing. And so there a few examples of this, not that many, it's not a very little paradigm, but it still has many interesting characteristics. So the first one was that human activity correlates usually with light. For the most part, when we go to the office and when we're doing something, our physical presence implies that there's going to be some light available because otherwise we wouldn't be able to see anything. So in these cases, when there is that alignment, having a solar cell allows us to then power a batteryless camera that will be able to take pictures using that same light that the environment was providing. So you have this nice source of the purple arrows or the energy path, and the blue arrows, the information path. So we have this nice correlation. And there, it saves you the battery, because even if your camera had the battery, it doesn't make sense to take pictures of dark rooms, right? So you're really only interested when the information is available, and then that same light can help you power your device. There are other examples. Another one is when you have a piezoelectric source that generates electricity when it's deformed, so when there's movement, when there's vibration, and then you can use that same primary energy to gather information from the event that is generating the vibration. Right, so there are a few of these examples, but even just the first one of correlating with human activity is a fairly big one with the applications that I've developed later on. So I've mentioned so far just the primary energy that is available, right, from indoor environments. But to be able to run applications on this without a battery, we need to do certain things. And to decouple them, I worked on something that I called the Energy Management Unit, or the EMU. And so this is a block that sits between the transducer, which can be highly variable in the amount of electricity that it produces, and then the application, which is usually rather deterministic in the amount of in the amount of current that it consumes and at what voltage it consumes. So by having this block in the middle, we can fully decouple the transducer such that you can operate each of them, the transducer and the application, at their own voltage and at their own current. So on the input side, we have a boost converter, which allows us to guarantee that we have this maximum power point tracking, which maximizes the input from the environment by adjusting the impedance and maximizing the power transfer. On the consumption side, we have a buck converter that allows us to have feedback control, so that on our application, we can do something like DVFS, so that we can dynamically adjust the voltage independent from the transducer itself. And then the glue that holds it together is this optimized capacitor in the middle. I call it optimized because to really get the best results in terms of response time, you have to reduce it to the minimum that you need to accommodate your Q, your energy cycle. And so when you have the smallest capacitor that you need to guarantee the energy that you need for your application, this then minimizes the startup time. You can think of it as, you know, the RC constant in when you're charging up a capacitor. So the smaller the capacitor, the faster it will charge up. But we still have to guarantee certain levels of, or a certain amount of energy so that we can have an application that executes reliably. So with this EMU, we did many different types of tests with different components, and it's a very flexible a very flexible block because it allows you to hook up to many different types of transducers. If you have a rectifier, you can also use AC sources. And in general, you need very little amount of power. You need at least 5 microwatts before the EMU can actually turn on by itself and start doing all the different things it does, regulating and impedance managing, etc. There is an upper limit because otherwise things will burn, but it's fairly high, 500 microwatts. And then we do have to pay a price for all of these nice things that we get with the decoupling, and that comes in energy efficiency. So energy efficiency, because we have certain regulators, it's going to be less than 1, but from our tests, it's very close to 90, especially when you use something like a buck converter, which is highly efficient, especially in the active regions when our current consumption is fairly high, and that's what would generate the energy consumption. So it's a very high, end-to-end energy efficiency. But what's really then the really key aspects of this is that we can guarantee reliable execution because we have a capacitor that can store a certain amount of energy. So let me go into details about this reliable execution because it's really what allows us to have interesting applications that operate batterylessly. So when we talk about reliable execution, we have to talk about atomicity and what does it mean to execute an atomic task. So we're going to do this with an example. So this is a platform that we built. It's a Bluetooth temperature sensor that is batteryless. It has a low power microcontroller that also has an integrated radio. And when we implement this simple application of really just turning on and broadcasting BLE packets, we have a power trace that looks like this. This is a power trace done with the rocket logger. So you see then the different the different phases. In the bottom, LPM means low power. And then there's a trigger, which means that this is a signal from the EMU saying, okay, I have enough energy. And then the microcontroller can turn on, you configure its peripherals, and there you see 3 peaks. These are the 3 BLE packets that we broadcast in the 3 different advertisement channels for BLE. And then we go back to low power mode. So here, when we integrate this, when we take a look at how much energy it needed to do this simple task of transmitting the 3 BLE beacons, the probability density function looks something like this. It's a very narrow peak around 108.2 microjoules. Right? So microjoules, it's a very small number. And so this is the probability density function. When we look at the cumulative density function, it looks something like this. It's a little bit like a step function. And one way of interpreting this CDF is the probability of success when you have an energy storage of a certain size. So if you go on, let's say on the left, if we have an energy storage device that can only store 50 microjoules, the probability of success is 0, because as soon as we are somewhere in the middle of the execution, we run out of energy and everything shuts down. But so it's only when we have this little cumulative density function reach 1, where we're sure that at that energy storage size, we will always be able to execute our atomic task. And this is what I call the batteryless limit, which is the maximum energy storage you should have for something to be batteryless. So in the strictest sense, anything bigger than that is just luxury. You don't really need it for functionality. And it's something that I want to avoid. I want to minimize. I always want to be in that little sweet spot, because when you're in this little sweet spot, and in this particular case for this application, it was 109 microjoules. So if your EMU can store up to 109 microjoules, you have reliable operation, but you also have this minimized startup time. So you have the smallest capacitor that you need, which means that it will wake up the fastest. And just to give you a notion of how this system would behave in, for example, in my office, we would have in one single day around 28,000 activations. So it can, for the normal 8 hours, the one a postdoc like myself now would have. So I would only work for 8 hours, and during those 8 hours, I would approximately get 1 activation per second. So 1 activation means 3 packets per second. So it's a fairly good activation rate for being batteryless and being powered only from indoor lighting. So this, if you're interested, this platform is also open source from the Computer Engineering Lab website. So, okay, that first application is fairly simple, right? It's really the simplest thing you can do for, for an application, just broadcasting a constant packet. But can we do something more interesting, right? So we wanted to do something that would allow us to estimate the occupancy level in an office. So this is an application that required some a bit different hardware. So here we had a microcontroller that was a little bit more powerful, the Cortex M4. We had also we wanted to use a thermal camera for privacy reasons, but we also have an EMU in that board, and let's say the transducer is actually even the same. So for this application, if we look at the high-level tasks that we need to do, we have three. First, take the thermal picture, then run some CNN that could allow us to estimate count the number of heads, for example, to estimate how many people were in that room, and then transmit that result via BLE. So if you look at those three tasks, acquiring an image and sending a single packet, they're atomic because you have to complete them once you start. You cannot pause in the middle of taking a picture, because then it loses meaning, the picture itself. But the head detection part, that's something that is purely processing, and as such, you can execute it non-atomically, which means you can do checkpoints, you can stop it at a certain point and pick it up much later, and the end result is not going to be different. So what's really nice about this application that fits within the tight energy constraints of energy harvesting is that it compresses significantly. So if you take a picture from this camera, it's almost 10 kilobytes of data. And after we do the processing, if we're only interested in the number of heads that were found in that picture, it can compress that down to a single byte. So it's a fairly good compression, and it fits very nicely into this, this general paradigm of doing as much processing as you can locally, so that you minimize the communication. So let me just give you this example walkthrough of how we did this head detection. So the first thing, we have a small binary detector, which takes a small chunk of the picture, and it just asks the question, is there a head in this little patch, yes or no? And then we go through the image at a certain stride. And at the end, when we scan the whole image, you will have something like this. You will have heads that are detected from multiple patches, and then to fix this, you need to do something called non-maximum suppression, which collapses overlapping detections into a single head. And then once you do all that, then you need to count the remaining number of detections, and this will be then your final number. To do all of this, we ended up needing 5,000 tasks to be able to do all of this. Right? So a task is just a small unit of computation, which will take, like the small patch of image and do the detection. So this is a fairly large number of tasks. And when we think about how to execute all those different tasks, right, we have the 5,000 processing plus the image acquisition plus the transmission. And when we think how to execute this batterylessly, we can think of two very trivial approaches. The first one is to say, okay, even if I have 5,000 tasks, I'm only going to draw 4 here just to make it readable. I can just execute all of them together in a single energy cycle or a single energy burst. So in a single activation, I will execute all 4. Okay, that's one approach. The second approach is, okay, let's just take it one task at a time. So I'm going to take the first task, and I'm going to save those results to non-volatile memory. I need to go to non-volatile memory because it's a batteryless system, which means that it can lose its voltage, it can go down to 0, and I don't want to lose all of the information, so I have to record it in non-volatile memory. And then I need to, when I go to execute task number 2, I need to load my energy from non-volatile to volatile domain, do the processing, and then save everything back to non-volatile memory. So these 2 approaches are going to have different types of overhead. So there are different overheads that come from your energy storage. So if you need a big energy storage device, it's going to have a large RC constant, which means that it's going to take a very long time to wake up from 0. Then another one is boot up. So every time you turn on, you have to pay a cost. And then the other one is saving and restoring of non-volatile data, right? So reading and writing into non-volatile memory is something that can be quite expensive. So if we look at those two approaches, the first one has the problem that it has a very large energy cycle. So if executing all of those 5,000 something tasks consumes a lot of energy, we're going to need a super cap. And then we're back to the problem of having a large energy storage that will take a very long time to go from 0 to fully charged. If we have the second approach in the bottom, then the problem is that the overhead is going to be way too big, because we would need to save and restore a lot of data from the non-volatile memory after each task. And this is particularly tricky because if you don't know what data you need, you have to save all of your data. And so if you save the whole full picture the whole time on all your stack, it's going to add up to a lot of data that you need to constantly save and restore. So we looked at this question and we wanted to optimize this total cost. And so to do this, we wanted to, do a formal formulation of an optimization and to be able to come to a solution. But to do this, we first needed to have a special model. And Julianing is the general work that we did to solve this. And this has a very specific system model. So the first one is that we need to have a very special programming model for the programmers. So the programmers need to be very careful when they write their dependencies from the different tasks. And they have to very clearly identify what is the output from certain tasks and how they and what are the inputs that are needed for those specific tasks. So this is something that was done in a research group with a framework called Ladybirds, which was, let's say, an extension of different programming models that were done in Professor Thiele's group, where the programmer needed to very explicitly put these data input and output data dependencies. So because the nice thing about this is when the programmer takes this effort, we can then easily compute an application task graph, which allows us to draw this graph of the different tasks and their specific data dependencies. And this is going to be very important because it will allow us to optimize the data that we load and restore from the non-volatile memory. So our energy model takes into account different things. So first is the amount of energy that a single task requires to execute. And the best way, or I would say a good tested way to do this is if you can do this experimentally. And so we do require some sort of energy characterization to determine how much energy our little kernel requires. And then we have what turns out to be a fairly simple linear model for the energy overhead, which is related to just how much data you need to save or to read or write from the non-volatile memory. And then because we're using some special FRAM, external FRAM component, then the read and write energy is slightly different. So we need to take them into account separately. So our general approach with Julianing was to have this Ladybirds application. Ladybirds is this specialized framework. And we would put this into an optimization model combined with the energy costs, which are tied to a specific platform. And then this additional parameter called Qmax, which is the maximum limit that we would allow for it's kind of like the burst size. What is the maximum amount of energy that we allow the system to execute at once? And then from this, we would be able to generate code that is specific to the platform that we were looking at, which is a platform from NXP. This was done in collaboration with NXP. So our optimization problem then looks like this. Minimum, we want to minimize the total. And then the first bound is that our Q, so our energy burst size, has to be smaller than this Qmax, so smaller than the limit. Let me now refine a little bit into this model, because we can actually do design space exploration when we have these different parameters. So we will have then an application which has a certain amount of tasks and certain dependencies, and we're very interested in this domain space. So the first, the x-axis is Q, so the energy burst size. How much energy do we need to execute this atomic task? And then the y-axis is the total energy costs, including the read write and including the boot up and all the other parameters that I mentioned. So the two approaches that we looked at before look something like this. When we have the joint task, so everything at once, we need a fairly large amount of energy storage, but we have the least amount of cost. On the contrary, we have the single task approach, which has a very reduced storage requirement because we only need to guarantee a single task executes, but it has the largest cost because of this reading and writing to non-volatile memory. So in general, when we have this application and we want to be able to, so first, sorry, I just want to point out that there is an infeasible region, because if your queue is too small, queue 0, then you really won't be able to store any energy. So you need to also take into account the minimum bound. So in the end, our optimization problems looks like this. We want to minimize the cost, and we want our queue to be at least big enough so that we can guarantee the atomic executions, which include booting up, running our task, and saving the energy that we need for storing it into non-volatile memory. And then the maximum is we wouldn't need to have more than the full application. So let me show you how this tuning this Q max looks like. When our Q max is fairly large, so say we have a battery, we would hope that our optimization formulation will result in this result, because doing everything joined without going to non-volatile memory, that's the optimal solution. And so we would have the lowest energy. And that's fairly, let's say, it's groundbreaking, right? But the interesting part then is what happens when our Qmax lies somewhere in between. So it's less than our entire application, but it's naturally bigger than the biggest task that you need to guarantee. So this is then where it gets interesting, and this is the hard problem. And ideally, we would find hopefully somewhere that is lower Q, but it can be on the line Q, and the total energy cost, it's going to be certainly higher than the joint task. I think there's a question.
Oh, yes. So I hope I can interrupt and ask a question here.
Yes.
When you look at the cost, actually had some discussions with Roman Jakob 2 years ago about similar subjects here. If I understood him correctly, you actually turn off the complete system, even if you use the non-volatile memory, right? So when you turn the system off, actually the operating system, so the whole microcontroller has to be rebooted when you restart. If you look into the case that you can preserve your state in the FRAM, and then you can restart directly from the status before you turn the system off. And this could reduce the energy consumption to avoid the overheads for rebooting.
Yes, I'm not sure if I followed, but were you referring to a microcontroller that has on-chip FRAM?
Yes.
Okay, so then yes, but the only one that I know is the MSP430 FR blah blah.
Yeah. Yes.
And the problem with that is that it's a PI core, right? So it's 16 bits,
that's right.
And it has a very limited on-chip memory.
So I actually have the next question. You mentioned that this is an external FRAM. Could you be more precise about the architecture here? Because my group has spent some effort trying to make FRAM working with multi-core systems, and seems that there's still some effort to do. Yeah.
Yes. So the reason, there are multiple reasons why we ended up going with an external FRAM chip. The cleanest answer is that we want to be fully interoperable. And also we want to be able to have larger models that perhaps don't always fit within the on-chip FRAM of the MSP. So then as we dig a little bit deeper. So the reasons why FRAM is not available on-chip everywhere, and it has to do with economics and with commercial interests, right? So it's a patented technology only from Texas, and it's not then widely available. And there are also costs with the process and things like this. So the reality to this day is that for 99% of microcontrollers out there, flash is still king. And when you have then this, let's say, I wouldn't call it restriction, but you have this property, then on chip, you really only have flash, it then becomes almost a necessity to look for external components, because if you have flash, flash it's king because it's great. You need to program it once, and then reading is fairly cheap in terms of energy. and you don't lose the reliability if you're only reading. Right? The problem is writing. So with an external FRAM chip, what's nice is that we have full compatibility with all of those 99% of the microcontrollers out there. And this was then also part of a restriction from our partners. We were working with NXP, and naturally they wanted us to implement this application on an NXP microcontroller, which only had flash on chip. So the best way to save our data is to look, okay, what's the best option for an external component in terms of energy? And right now, with the commercial technologies that we have, it's the best one that we found was FRAM. There are many other technologies. Some of them are closer to mass production or not.
So you only use FRAM for data, not for instructions, right? If I understood
Correct.
it correct. Okay, thanks.
Yes. 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 So it's a normal the LPC 5400, I think. And so it has normal on-chip flash. So when it boots up, it's there. But we were saving our application data, our weights, and all of this on the external chip, an external FRAM chip, which is manufactured by Cypress, because Cypress has a licensing deal with Texas Instruments. So it's I forget the size, 2 megabit, maybe 2 megabit external FRAM, which we program or we access via SPI.
Thank you.
Sure. Okay, so then this is basically our design space exploration, which gives me, the designer, the liberty to select what my maximum Qmax is, right? And so this is a fairly flexible framework that can let me fine tune if I need to have some restrictions based on specific components. So, for example, ceramic capacitors have a fairly low limit of capacitance that they can hold, and so then I can fine tune this. Or if I want to go to other types of capacitor technologies, I might increase my Qmax. But with this, I have full liberty as a designer to choose what my restrictions from my energy storage are, and the framework then will find the optimal way to organize my tasks so that I have the lowest energy overhead for this particular restriction. So I want to just show you real quickly what our solution is like, this Julianing our whole optimization flow. So we start from a schedule, which is given by the application, sorry, by the programmer, because we run single core applications. And for this example, I'm going to use 3 simple tasks, and they have then just simple data dependencies between task 1 and task 2, and then another dependency between task 2 and task 3. So from this schedule, then we transform this into a state diagram. And this state diagram has a specific meaning. So the first meaning is that state 0 is before the application starts execution, and task 3 is the end of the application. So after all of the tasks have been executed. And so from the beginning, we built this graph by annotating all these different edges. And the edges represent an energy burst, which executes a particular task, and the saving or reading from the data dependency. So just to give you an example, the simplest one of executing everything at once is represented by the brown edge in the bottom. I don't know if you can see it, sorry. Oh, okay. I had it set up in my other computer. So here I can only describe the color. So if you have this brown color, you see that it goes in one single step from state 0 to the state 3. And in the edge, it says T1, T2, and T3, which means all of those 3 were executed once. You don't then need to save anything, and then that's fine. The opposite approach, to execute a single thing at a time, is taken by those pink edges. So you have to go through all the states. You have to go from state 0 to 1, which executes task 1 and saves the data output from task 1, which is DA. Then you have to go from state 1 to state 2, which loads data A, executes task T2, and then saves data B. And hopefully you get then the notation to understand the different edges. So once we have this first state graph, we then prune the graph so that we can take out all of the edges whose energy is bigger than a restriction. And this cuts out a lot of the edges from the graph, especially when you have a very large graph and we have a fairly low Qmax. And then once we do this, we simply apply Dijkstra's algorithm to find the shortest path between state 0 and state 3. And then we know from Dijkstra this is an optimal to find the shortest path, and it has a fairly nice runtime. It doesn't explode, it's not exponential. What's then even nicer is when we formulate the problem like this, is that we get two interesting results. The first one is the minimum E total. So that's the total energy that was required to execute the entire application. And this is the actual path itself. So if it was the single step from 0 to 3, then it would be just that edge. But if it's complicated, right, it would automatically tell us what the total energy was. But it also gives us the optimal size, which falls within this bound of less than Qmax and greater than the minimum. And this is the highest weighted average, or the maximum weighted edge, which is the maximum step that you need to take between two specific states. So this can also help us reduce our Q, our energy storage, even further from the standard bound of Qmax. So let me just show you then the results from this occupancy estimation. So when we had this approach of running the entire app at once, we were able to do this in a single burst. The other column, data transfer of 0, because we didn't need to save anything. Everything was finished at the end of the single burst. The total energy was 2.2 joules per image. So one single image processing and transmission took the 2.92 joules. And our energy storage needs is in fact the whole number is 2.92, because we're doing everything at once. When we take the opposite approach of doing only a single task at a time, we needed to have 5,000, almost 5,500 bursts, because we're doing one at a time. Our data transfer is huge because we took this as the developer doesn't know which data to save. So we were transferring all of the data that we need for processing for every single burst, which ends up being a huge number. And when we add up the energy required for processing a single image using that approach, it's 4.68, which is significantly worse than before. And our energy storage then it's significantly better. And this is because in the single task approach, you really only need to guarantee that you can take the thermal picture and save the results into non-volatile memory. So that's very low. So you see then the two extreme points in the Pareto curve. But now with Julianing, we rerun it again, and we actually do take that same Q from before, the 131 millijoules, which comes from the thermal energy. And we're able to, our optimization algorithm tells us that the minimum burst that you need is 18, which is really good. We do need to have some data transfer because we are saving only the data that we need according to the task dependencies. And then our total energy per image is very, very close to executing the whole app. You can see that it's only 2 millijoules more, which is tied to this turning on and off and then saving and restoring the data from non-volatile memory. But then you can see that we're very good on both the total energy cost as well as the energy storage, which is then precisely what we were looking for. Right. So with this approach with Julianing, we really get a very good result for both the energy storage bound when we select the Qmax properly, and it will minimize the overhead for this Qmax that we selected. Right. Just to then also to clarify, if our Qmax was 3 joules, the result is the top one, right? The whole executing the whole application at once. Okay, so I'm running a little bit late on time, but I'll want to talk a little bit about my more recent work. And this is beaconing. So beaconing, if you think of the traditional sense of beaconing, it relates to communication between your smartphone and a building. And it helps make different stores or environments smarter, because you can, if you have the right app on your cell phone, then you can do different things. You can do course localization based on beacons. And then you can do customer registration, you can do payment services, and you can do many different types of things if your store supports this. When we take this approach of batteryless systems, I like to think of them, or one way to use them is to use them as a batteryless fount of information. And when you have this, and it's building to phone communication only in one way. And when you have this this sensor board, this was the BLE board, and when the lights are off in your building, the thing is powered down, it's not doing anything. When the lights are on, then this device very quickly reacts, turns on, and you can do then your environmental data, your localization info. And as a user, then if you have your cell phone, you can gather data from this sensor that is out there, and you can check different things, environmental conditions, or more information from that specific location. Now, we've taken this a bit further, this batteryless notion, and we've created the batteryless meter card. So this is some work that I started towards the end of my stay at Mito Miko. That's why it's called the Mito card. And it's a card to building communication. That's how we're trying to place it. So it's a bit more refined than before. You see the difference between a research prototype and then a commercial prototype. So this is something that uses some special components. We use organic photovoltaics to have a very thin film solar cell. The whole device is less than 2 millimeters thick. The area is smaller than a credit card. And then we can do fun applications with its nice features, right? So we can also have sensors in there. But the way I think of it is that it's something kind of like RFID, but much better in different scenarios. First, it's much more powerful. We can have sensors. We can communicate with BLE. We can interact with an accelerometer on a device. And it also has this nice feature of being privacy enabled. And by this, what I mean is that a batteryless device, when it's in your pocket, it's not possible to turn it on remotely. There's no way that light could go through clothes and turn into your wallet. So it's as opposed to an RFID, which if you're not careful, can be remotely powered. This device is indeed much more privacy enabled, much more secure than a normal RFID card. And this is also open source. You can go to mitocard.swiss. You can download the hardware, the software, and you can play around with it yourself. This is something that I am continuously working on to this day. And to just give you a little hint of what I'm working on is I'm working a bit more on the application side of batteryless systems. I'm extending this to the Web of Things. If you haven't heard of the Web of Things, it's the extension of the Internet of Things, which doesn't have any, or only has standardization up to layer 6 or even lower. So if you have IP, you have things like 6LoWPAN and Zigbee and whatnot. But it doesn't really help you integrate many large systems. So the Web of Things aims to take some of those web technologies, adapts them to very low power systems, and then we can still reap the benefits of these protocols that are have been tested and proven at an internet scale. So this is one of my last slides. Going towards the future, where I see this technology developing is a little bit closer towards what I call my ideal card. So this is a little mock-up that I did from a card that will have a solar cell. It can also have a little fingerprint sensor there. So the fact that it's powered by light gives us this nice privacy-oriented features. But because it's also a BLE, then it can communicate with standard infrastructure. It might even connect to the internet. We can use it for different, for different things like authenticating web sessions or integrating or facilitating it with user localization. And in general, this Web of Things perspective is what I'm now actively working on now. In doing so, in batteryless technologies, we really can make this claim that it's low cost, right? It's very thin, and it doesn't require harmful materials that have a huge environmental impact. So that's it. It's been a long road for not quite 10 years, as Dava said earlier, a bit less. But it's been a long road through many different prototypes. I talked only about a few of them. And naturally, this is not something I've done alone. This has taken many heads to think about these things, not just from my research days with my different research groups, but also with different companies that have been taking this technology and bringing it closer to market and to apply to different technologies and applications. So that's it from my side. If you have more questions, then I'm happy to. I hope it wasn't too long.
Thank you very much, Andrés.